Welcome to Lecture 26, in which we will begin to discuss the design of sequential circuits. As we talked about in class last time, a sequential circuit can be used to detect certain sequences. What I mean by this is the following. Let's say that we had the input sequence 0, 0, 0, 1, 1, 0, 1, 0. And suppose that we had a sequence detector that would output a 1, and we've been calling our output Z, so I'll put Z here. But suppose that we had a sequence or sequential circuit that had been designed to detect the sequence 0, 1, to output a 1 whenever the last two inputs were 0, 1, and to put out a 0 otherwise. Then this the way that this would work is it would output a 0 in all of these cases, but in when we get this first 1, since the last two inputs were 0 and 1, it would output a 1 here, and then 0, 0, 1, 0. So we would like to figure out how to design a sequential circuit that would act in that way. And so let's think about how we might do that. You can think of this as doing our analysis backwards. What I mean is that during the last two lectures we've talked about how to analyze the behavior of a sequential circuit, and now we're going to do that analysis backwards. And so you will recall that the last thing that we've done in each case is the graph, and so the state graph. And so now the state graph, since we're going backwards, the state graph will be the first thing that we'll do. So let's think about this. So we want to, our goal is to output 1 whenever the present input and the last input are the sequence. Actually, I should probably say whenever the last input and the present input are the sequence 0, 1, and output 0 at all other times. Okay, so now before we can make a state graph for this, we need to define some states, and I'm going to first start in this way. So we'll say define states. Now I'm going to go ahead and give you a hint that what I'm going to do right now is going to be preliminary, and it's not going to be the way that we want to do it in the end, but I want to show you, basically you might say, the wrong way first, and then we'll come back and do it the better way. So one way that we might think of defining states is the following. We might define state S0 as no input has yet been received. So I'll come down here, and here would be S0, and that's the state where we haven't had any inputs yet at all. Now, if we're in that state, then obviously from that state we can go to two possible states. We could go to S1, which means the only input received is 0, or S2, the only input received is 1. So this would be, we would put a 0 here, since S1 is the state we go to if we receive a 0. And for S2, we would put a 1. And in both cases, since there has been no previous input, that means we've only received one input, so we couldn't have possibly received that desired sequence of 0, 1 yet, since that's a sequence involving 2 inputs. And therefore, since we're supposed to output 0 at all other times except when we see that sequence 0, 1, we would output a 0 in both of these cases. And that defines states S1 and S2. Now, from S1, now remember, S1 is the state that we have received one input only, and it's a 0. From that state, we could go to two other states. We could go to S3, and let's define S3 as the state, meaning the last two, or the last input and the present input form the sequence 0, 0. Now, if that is the case, then we know that since 0, 0 does not match the desired sequence, we'll output a 0. So 0, 0 would be what we would put in this line leading to S3. S4, and I'll be looking ahead now. Now, another thing we could do, if we're here in state S1, which is the state that we get if we've received 1, 0, if instead of the second input being 0, if the second input is 1, then we would go to S4. So S4 here is defined as the last input and the present input form the sequence 0, 1. Now, since that is the desired input, we would output a 1 in that case. So we have 1-1. Now, what about S2? Well, S2 is the state that we've received one input and it was equal to 1. And so if we're in S2 and we receive a 0, that would take us to S5. And that would mean that the last input and the present input form the sequence 1, 0. And since that's not our desired sequence, we'll output a 0 in that case. And then for S6, that would be where we would go if we get a 1, and that's the state, the last input and the present input form the sequence 1, 1. And since that's not the desired sequence, we'll also output a 0 there. And now, to finish up this graph, we need to figure out where we would go from each one of those states. Now think about it. If we're in S3, which means that the last input and the present input are 0, 0, and we get a 0, then the last two inputs would also be 0, 0. So if we're in S3 and we get a 0, we output a 0 and stay in S3. On the other hand, if we're in S3, which is 0, 0, and we get a 1, then in that case the last two inputs are 0, 1, and so in that case we would go to S4. That's if we have an input of 1. We would go to S4, which is 0, 1, and since that is the desired sequence, we'll output a 1. Now, what about if we're in S4, where the last two inputs are 0, 1? Well, if we're in S4 and we get a 0, then the last two inputs would be 1, 0, which is S5. So, 0. And since that means that the last two inputs were 1, 0, and that's not the desired sequence, I'll put a 0. And on the other hand, if we're in S4 and we get a 1, then the last two inputs are 1, 1, and so we'll go down to S6 in that case. And 1, 1 is not the desired sequence, so we have 1, 0. Now, what about if we're in S5? Where if we're in S5 and we get a 0, that will mean that the last two inputs were 0, 0, which puts us up into S3. So we would have this 0, 0. And on the other hand, if we're in S5 and we get a 1, then the last two inputs would be 0, 1, which matches S4. So we put a 1 there, and we also have we want to output a 1 in that case because the last two inputs would be 0, 1. Finally, if we're in S6 and we get a 0, that means that the last two inputs were 1, 0, so that puts us up into S5, 0, 0. And if we're in S6 and we get an input of 1, then we stay in S6 because the last two inputs would still be 1. So 1, 0. And this would complete the state graph. And notice that as must be the case, whenever you want to check this, one way to check a state graph, I mean, this is a preliminary check. It doesn't guarantee you that it's correct, but it is something that must be true, or else you can immediately say it's wrong, is that the number of arrows leaving each state must be 2 to the n, where n is the number of inputs. And since we have one input here, just the input variable x, 2 to the first power is 2, so we must have 2 arrows leaving every state. And if you look here, we have 2 arrows leaving S0, 2 arrows leaving S1, 2 arrows leaving S2. Here's one arrow and another one leaving S3, so that's 2 arrows from S3. Here's these 2 arrows leaving S4, this arrow and this arrow leaving S5, and finally this arrow and this arrow leaving S6. And so we do indeed have 2 arrows leaving each state, and I believe that this state graph is correct. However, the inconvenient thing about this state graph is that it has 7 states, and this is more than we would prefer, and it's more than we're accustomed to dealing with in our previous problems. And it turns out that there is a way to do this problem. If we just make one small assumption, there is a way for us to do this problem with considerably fewer states. So again, what we have here is technically correct, but there is a way for us to do this that is more efficient. And so that way is to make one small change in the statement of the problem, and that is this. Assume, so I'll say, in order to reduce the number of states needed, let's assume that there there has been at least one previous input to the circuit actually, let's say there have been at least two previous inputs to the circuit, and that the most recent two inputs form the sequence 0, 0. And practically speaking, the way that you could handle this is, we're going to get a circuit now, and if you wanted to use it to detect the 0, 1 sequence, you just need to you might think of it as priming it. You need to put in a couple of zeros first before you start the signal that you want to look at for detecting that sequence 0, 1. So you would just prime it, put in a couple of zeros, or if you wanted to, you could put in more than two, but put in at least two, and then you'd be in good shape. So if we work with this assumption that we have received previous inputs and the last two inputs were zeros, then we can define our states in this way. So we'll say, so now we define our states in the following way. And we're going to see that we'll come up with fewer states than we did before. Well, S0 will be the state that the last two inputs form the sequence 0, 0. And I think you can clearly see then what we want for the others. For S1, we'll have the last two inputs form the sequence 0, 1. The last two inputs form the sequence 1, 0. And the last two inputs form the sequence 1, 1. And this will cover all of the possibilities, and now you see that we've gone from a system with 7 states to one with just 4. And that's really nice, because now we will be able to handle this with just 2 flip-flops. So let's see how this goes, okay? We have S0 here, which means that the last two inputs were 0, 0, 0. Now, if we're in S0 and we get another 0, then of course we'll stay in S0, because if we append another 0 at the end of this 0, 0, then the last two inputs would still be 0, 0. And so we have 0 and output of 0. But if we're in S0 and we get a 1, we'll go to S1. And not only that, but we want to output a 1 in that case, because 0, 1 is the desired sequence. So we'll have 1, 1. Now, let's suppose we're in S1 and we get a 0. Well, if we're in S1 and we get a 0, then the last two inputs would be 1, 0. So 0. Now, 1, 0 is not the desired sequence, so we'll output a 0. but we'll go to S2. And on the other hand, if we're in S1 and we get a 1, then if you look at appending a 1 here, the last two inputs would be 1, 1, which would be S3. So I'll put S3 right here, and 1. Now 1, 1 does not match the desired sequence, so we'll put 1 and 0. Now, notice at this point we're not done, because we have two arrows coming out of S0, two arrows coming out of S1, but no arrows coming out of S2 or S3, so we need to consider those two cases. Now, so suppose we're in S2, which is the state that the last two inputs were 1, 0, and we get a 0. Then that would mean that the last two inputs were 0, 0, which would take us to S0. So we'll draw an arrow like this, and of course if that happened, we would output a 0, because 0, 0 does not match the desired sequence. On the other hand, if we're in S2 and we get a 1, then the last two inputs would be 0, 1, and that matches, that takes us to S1. And not only would it take us to S1, but it also gives us an output of 1, because 0, 1 is that desired sequence. So we'll say 1, 1. So now there's two arrows leaving S2. And to finish this up now, we need to look at the two arrows leaving S3. If we're in S3, which is 1, 1, and we get a 0, we'll go to S2. So 0 would take us to S2, and since 1, 0 does not match the desired sequence, we'll output a 0. And finally, if we're in S3 and we get a 1, that will then the last two inputs would be 1, 1 still. So we go back to S3 and output a 0. And now we see that we have two arrows coming out of each state, and this is the state graph of this new system, which is identical to the original system, except that we build in one more assumption, which is that the number, we assume that there have been at least two previous inputs to the circuit, and that the most recent two inputs form the sequence 0, 0. Okay, so with that assumption, we've now cut this down to just, as we can see from the picture, to just 4 states. And this is similar to the problems we've been doing in the last 2 lectures, so this can be handled with 2 flip-flops. So let's try to think about what our next step should be. Well, you will remember that when we were going in the forward direction, the next to last, the state graph was the last step, and the next to last step was the state table. So if we're going backwards now, it looks like the state table should be our next step. So let's say state table, and of course we have present state, next state, and output. Now the output is Z, and so let's see now how this will go. Okay, so our 4 states are S0, S1, S2, and S3. And we look up at our state graph here, and we see that if we're in S0 and the input is 0, we stay in S0. And we output a 0. On the other hand, if we're in S0, here, if we're in S0, let me just redo this first line to make sure everybody's with it. So what we've put in so far is if we're in S0 and our input is 0, we'll go to S0, so that's denoted here, and the output will be 0. So that's denoted here. Now, if we're in S0 and our input is 1, we will go to S1 and output a 1. So we put S1 here and 1 there. Now, what about for the next line? If we're in S1 and we get a 0, we go to S2 and output a 0. So S2 and output a 0. On the other hand, if we're in S1 and we get a 1, then we go to S3 and output a 0. S3, 0. What about S2 now? If we're in S2 and we get a 0, we'll go back to S0 and output a 0. So S0, 0. But if we're in S2 and we get an input of 1, then we will go to S1 and output a 1. S1, 1. Finally, if we're in S3 and we get a 0, we will go backwards to S2 and output a 0. S2, 0. And on the other hand, if we're in S3 and we get an input of 1, we'll stay in S3 and output a 0. So S3 and 0. And that concludes our state table for this problem. So now, again, thinking in a backwards fashion from what we did before, what came before the state table, and now will come after the state table, well, that's the transition table. Now, as we've already mentioned, well, let's do it maybe this way. We have present state, and we'll call it A, B. And then next state, which is A plus, B plus, and that will be for x equals 0 and x equals 1, and then we'll have output Z for x equals 0, x equals 1. Now, we're assuming now that we have two flip-flops, and that the output of one is called A and the output of the other is called B. And so we see that, as was the case in all of our previous problems, if we do have two flip-flops, then this would give us four states altogether: 0, 0, 0, 1, 1, 0, and 1, 1. And this is convenient because we have seen that we need four states for this problem. Now, I would recommend that you just go ahead and identify this first one as S0, the second one is S1, the third one is S2, and the last one is S3. Let's just, that makes it easier if we're consistent with that. And so now, if that's the case, then we can, by glancing up at the state table, we can see what we need here in the transition table. We would need, since we have S0 here, and we have identified S0 as being the 0, 0 state, then we would have 0, 0 here, and similarly 0, 1, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 1, and then the output is just the same as above. So 0, 0, 0, 0, 1, 0, 1, 0. And that completes the transition table. So we're getting very close now to being done, but this next step is going to be the trickiest one. Okay, you remember that in doing the analysis, just before the transition table, you have the excitation table. And so when you're doing the design procedure, the excitation table will come immediately after the transition table. But now we have a decision to make. We see the transitions in the transition table. We see the transitions that need to happen. We see what the next state should be given the present state and given the input. But we now need to make a decision, well, what kind of flip-flops are being used? Okay, so for the sake of this first problem, let's not make this too difficult. Let's maybe assume that we have D flip-flops. Okay, so now we need to figure out what our excitations should be. So we'll have our excitation table here, and we'll have let's say A, B, and then DA, DB, and of course the output Z, which is easy. We know what that will be. Now, before we proceed any further, let me just give you a warning. You remember that in the analysis step, it was when we went from the excitation table to the transition table That was the step that we found to be the most challenging. So in the design procedure, it'll be the backwards step that's the most challenging. In other words, going from the transition table to the excitation table. So we're going to need to be very careful, pay very careful attention as we do this next step. And so we'll see how it goes now. So we need to figure out what these excitations should be in order to cause these transitions to occur. So let's start off with A. Now this says that if A is 0 and X is equal to 0, then the next value of A will be 0. Now if we're dealing with a D flip-flop, actually I think I want to change something here, because D flip-flop, maybe I'll save that for you for your test, because D flip-flop is very easy. So let's work with something a little trickier. We'll say T flip-flop. Okay, so we'll work with the assumption that we have T flip-flops, and therefore this will be TA and TB. And then for your test questions, I'll have you redo this problem, but with the assumption of D flip-flops, because that should be very simple. Okay, so now let's resume this. So, again, when A is equal to 0, and of course B is equal to 0, and X is equal to 0, we want the next value of A to be 0. Now, the way to think about this is as follows. We know that A was equal to 0, and the next value of A is 0. And remember now, these are T flip-flops. Well, if TA were equal to 1 in this case, then we know that A would toggle, and so the next value of A would have been 1. But in fact it was 0, so that means that TA in this case must be 0. Now, what about the next one? Here, A is 0, and it goes to A equals 1, so A has toggled, and therefore T must be 1 in this case, T sub A. Here A is 1, and here A is 0, so A has toggled, and TA must be 1 in that case. And finally, here A is 1, and the next value of A is 1, so A has not changed, and therefore TA must be 0 in that case. Now let's look at the next column. A is 0, next value of A is 0, A has not changed, so TA must be 0. Here A is 0, and next value of A is 1. A has toggled, so TA must be 1. A is 1, next value of A is 0. A has toggled, so TA must be 1. And finally here, A is 1, next value of A is 1, so A has not toggled in this case, and TA must be 0. So that finishes all of the information for TA, the input to the T flip-flop for which the output is A. Now let's look at the other flip-flop. Let's look at TB. So if B is 0, next value of B is 0, and what will do that is if TB is 0, since B did not toggle. Here B is 1, Next value of B is 0. That means B is toggled, so TB is 1. Here, B is 0. Next value of B is 0, so B is not toggled, and therefore TB must be 0. And then down here we have B is 1. Next value of B is 0, so B has toggled, and therefore TB must be 1. And now finally, B goes from 0 to 1. It has toggled, and therefore TB must be 1. Here B goes from 1 to 1. It has not toggled, so TB must be 0. Here B goes from 0 to 1. It has toggled, so TB must be 1. And finally here B goes from 1 to 1. It has not toggled, so TB must be 0. And we can just copy down the output Z. 0, 1, 0, 0, 0, 1, 0, 0. So if any of that was difficult for you, I suggest that you just sort of go backwards now and make sure that with these excitations here, TA and TB, that we would get the transition table, if we were going, in this direction upward, that we would get the correct transitions. And for instance, if we're in A and TA is equal to 0, then the next value of A, if A is equal to 0 and TA is 0, then the next value of A should be 0, and that's consistent there. And you could check the others, and I think you'll conclude that we do have the right values here. So this is our excitation table. And so now the very last step is to try, well, almost last step. What we need to do now is to try to figure out what kind of circuit this should look like. We know we have two T flip-flops, but we need to figure out how TA and TB are related to A, B, and X. So we'll say, in order to draw the circuit, we need to find out how TA and TB are related to A, B, and X. Since this lecture now is into its 44th minute, what I think I'll do is just stop right here, and I'll go ahead and make up some problems for this lecture 26, and then lecture 27 will begin at the end of this one. So we'll talk now about the test. So now to take a look at the test for this lecture, has already been hinted. What we'll do in this test is we'll assume that we have exactly the same problem as what we just discussed in the lecture, except that now we're using D flip-flops rather than T flip-flops. And so this will cause a change in the excitation table, and therefore, and I want you to figure out what this new excitation table will be. And similar to what we've done in our previous two tests, I've given you a table here, and I have given you a few values in it, 0, 1, 0, and 1 here. I've given you these numbers along this diagonal, and the other numbers, alpha, beta, delta, gamma, theta, phi, lambda, sigma, tau, epsilon, mu, and omega. So I simply want you to figure out here, 26.1 says what are alpha and beta respectively. That means in order So what is alpha and what is beta? Is it 0, 0? That would mean alpha is 0 and beta is 0, or alpha is 0, beta is 1, alpha is 1, beta is 0, or alpha is 1 and beta is 1. That's what that means. You choose which one of those is correct. And here, what are lambda and tau, respectively? So lambda 0, tau is 0, lambda is 0 and tau is 1, lambda is 1 and tau is 0, or lambda is 1 and tau is 1. And finally, as you would expect, 26.3 will be given in class. So that will conclude lecture 26, and then in lecture 27, we'll come back up to this point where we have the excitation table for our original problem, and we want to now figure out, as is stated right here, in order to draw the circuit, we need to find out how TA and TB are related to AB and X. So that will be our first step in the next lecture, but you don't need to worry about that yet. You just need to worry about this test problem, which is to find out what the excitation table would be if we had D flip-flops rather than T flip-flops. So that's it, and good luck.